Once again, Roger of MudFossil University, and today we are going back to the basics. Now, I've been it's been years I've been doing this, and I sort of figured everybody had understood the basics of mud fossils, but everybody comes along at their own pace, so let's go back to the beginning and discuss on how this happens, because I know a lot of people say, oh, how can things turn into stone when they're flesh? So I'll explain that, but before I start, I was sent this today by one of my, mud fossil people, and the questioning whether or not this was something to do with cave art and what the whole story behind this is. So I'm going to try to explain this to you. This is in it's where they're looking at the Neanderthals and they're thinking that they're very sophisticated cave artists, which they did fabulous work. Now, what they're looking at here is this is blood. Now, of course, this guy understood, the blood in mud fossils, and he looked at it and he said, very red, and how could this be? So I looked at it now, and I can tell this is extremely, I'm not certain of exactly the place in the body this is, but I can see all of the different biology that was here. It was some form of tendinous connective material. I'm sure that's what it was. Now, you can see it has a scaly effect to it now, like it's dried over and scabbed over. But when this work was done, my feeling was when these little red spots were done, they came up and they just tap, 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 put little holes, and then the blood came right out of those holes. And look at it, you can see, if you look carefully, you'll see all these little holes. You see the little holes there? Little dots. And I think that's what they did. They just almost like a tattoo. And the blood ran out just the way it does in a tattoo. Only it has stained the surface, and it's red blood, it's arterial blood. And so there's other areas where you have the dark black looking bloods. And that's just what it is. That's how mud fossils are. And when they were originally drying out after the Great Flood, they were literally moist. And down in South America and so forth, they were mining slabs of fresh meat. And then they would stack them up on those walls like putty. They would just sit together perfectly, not a crack in them. And then as soon as they dried out, they turned to stone. That is the nature. Now I'm going to explain the process. All right, as I go into this, I'm going to keep talking chemistry, because your entire life is chemistry. That's all you are, is a chemistry set. And you process the stuff you take in, and if you don't process it correctly, you're sick. And when you die, the minerals and the different molecules in your body will do one of two things. They will either stabilize and not explode and rot away and be eaten by bacteria, or they will be rotted away and eaten by bacteria. So let's discuss what happens in mud fossils. Mud fossils are the product of a flood. All right, just remember that. But you soak them in wet fluid in a solution, just like in the ocean, for maybe years. All right, I'm talking about the Great Flood now. That was 4,300 years ago, and it's recorded everywhere, so don't tell me there's no flood. There was a flood, and it happened about 4,300 years ago, and everything pretty much drowned. And there was giants, and there was all that stuff they talked about. Now, when they drowned, what happened to them is the volatile organic stuff, which makes you explode. Literally, your body explodes. If you ever see those old battlefield pictures of Civil War and of bloated bodies and all that, that is what happens to your body. The gases in your body have no way to work themselves out into the environment, and they literally explode your body. The cells explode. And at that point, the fluids and so forth are pushed out through the areas in your body that are arterial areas, because there's no restriction on arteries. So the pressure blows that fluids out of anywhere the arteries are closest to the surface, and that in your orifices, in your eyes, and your nose, and all of those things. Now, when you are in a flood, however, different story. You don't bloat, you don't explode. Those volatile things, those explosive things, go into solution. That means that the water that you are in works its way through your body and works into the system to take these things out of your system and go into solution in the waters. And they collect in the waters like a gigantic bathtub ring. And that's what happened. The earth had a bathtub ring at that point. And what will come out into the waters is clays and transition metals, including iridium. And I have a story about this later, about the bathtub ring around the earth from the Great Flood. Now, so you're in the water, you're drowned, you're dead, your fluids in your body no longer circulate. So at this point, the waters start to invade and to take out the stuff that's trying to get its way out of there. It's called carboxylation. We'll go into that in a minute. Now, so you're in the water, you're in the flood, you're dead, you end up getting waterlogged. Waterlogged means take all of the stuff that is going to explode out and leave the guy's ball of flesh left. It's, the meat and the bones and the flesh and the skin and all that stuff stays. Now, eventually, the floodwaters go away. Now, two things can happen. You can be impacted in mud deeply, or you can be completely out of the mud and just laying there. And that was the case, I have found, in 90% of the rocks, which are all over the earth, were literally alive at one time. They were all pretty much body parts. And they were preserved in this manner. After the water ran off, they just simply dried out. That's the nature of a mud fossil. Now, so if it was in the wet mud, deep in the wet mud, you get different kind of effects. You get this kind of stuff where it's brown and muddy, and the ferrous oxides are showing up in here because it's been eroded away. That's a muscle bone. That's the muscle on the bone. That is the tendon that comes down, and that's the tendon that runs over to your finger. That is the fabric of the muscle that surrounds the bone. This side was eroded away. And that was from a giant hand, and I have the other parts of the hand and so forth. But my point being is there's 100,000 different ways the final product can come out. So we'll go over that. And it's a product of the transition metals. In certain waters, they will wash all that away and replace them with muds. In other areas, the transition metals will stabilize and you get fabulous colors. In opals, they stabilize in blood, and blood is literally completely packed with transition metals. So they take on fabulous colors. Now, carboxylation, this is important to understand. Carboxylation works with transition metals. Carboxylation is a process where these metal complexes, they call them, and they're transition metals, so they can hold on to something very lightly and then let it go, and then grab something else very lightly in a minor little transition, it's called. And that happens because there's a little extra pH or a little less pH. And it goes from like 7.4 up around your heart, and it goes down into 7.2 further down in your system, where it releases the oxygen. And then it picks up carbon dioxide at the 7.2 level, goes back up to the heart, and to where 7.4 is, releases the carbon dioxide, picks up the oxygen, and makes that circle. That's the transition. And you have almost 100 transition metals in you. And that is why you are healthy, is if all those are in there at the right places and at the right quantities, and they are grabbing a hold of a little glucose here and bring it down there and drop it off and pick up some uric acid over here. They know what to do, but they have to be there. And the reason those transition metals are in your blood system is because of bacteria that's in your body, in your colon and in that area. It processes the things that you take in and collects the metals. And if those bacteria aren't there, they cannot create the chemistry to do the job to get those metals. That's what they're for in your body. And you kill them with antibiotics. So you have to keep these bacteria, and every bacteria has its own special job. One of them might do gold, one of them might do silver, or the other one copper, or the other one magnesium. And you need every one of them. Don't let them, they're not just floating around in you for no reason whatsoever. They are there to carry a specific molecule to do a specific job. And if they're not there, your fingernails might fall out because that certain bacteria is not alive to create the metal that goes down to bring the stuff that makes your fingernails work. And they're that specific. Another one will be for your hair, another for your skin, another for oily pores, another one for saliva. I mean, it's that specific. If you don't have that stuff, people, oh, I got dry eyes. Well, I got sore toes. I got achy joints. I got no fingernails. My teeth are bad. My eyes don't work good. Every one of them needs to have service. And that service is just like oil in a car. Only you got 100 different types of oil. And if you don't have the right stuff in your body, you're going to be sick. That's it, case closed. And I always go into this because why not? Because all these rocks were healthy at one time because they were eaten from the ground. All right, now we eat from boxes of this and bags of that and fake this and that. And the things you put in your body don't just go in there and say, well, I'm not supposed to be here, let me just leave. No. They either break something in there or they attach to something they shouldn't be attached to. They're not just there benign. They don't go in and say, well, let me do a job preserving something in a box, and then when it gets into your body it has no effect whatsoever. It's insanity. So we should start thinking a little more about the things we put in our body, and the nature knows exactly what to do. If you eat healthy, you eat right from the ground, and you have a little bit of bacteria here and there coming off the skin of different vegetables. That's not going to hurt you. That's probably there for health reasons, to be perfectly honest with you. You're putting things in bleach to get all that stuff out and then skimming off all the chemicals that are in the skin. That's not the way to eat. Not in my world. And they say you eat 5 different colors at a time. And if you eat 5 different colors at a time, you have all kind of different transition metals going into you. And if they're in there and they're running the things around to your joints and your toenails and everything else, you're in good shape. You got a lot of better chance of being stay away from the doctor by doing that than just fast food is a slow death. Let me put it that way. So now, let's get back to this. Once you get this carboxylation takes all these things through your body. Once it stops, they have to settle and harden up or go away, and they stabilize. And how do they get stability? Is to find a molecule that wants to be with that other molecule, because everybody has that's their job. They grab and hold and let go, grab and hold and let go. Well, eventually they're dead, and when they can't grab and let go, they have to grab and hold. And that's stability. And stability comes usually from oxidation, primarily. And then there's other processes that metals and things come in and they attach. But primarily it's a drying out process, oxidation. All right, these are the different transition metals, and I've been talking about them. And they are the things that are in your blood, and those are the things that stabilize and lock other molecules and into these what they call metal complexes, and they become stable. You can break them back open again with acids, and then the blood and so forth will come back out of them, and the tissues will become flexible again. Now this is the breakdown of mud fossils. And clay, you see down here clay, mud and mudstone, that is your flesh and your red fleshy material. And then as it goes up, see slightly calcareous and mudstone, and then it goes into marl and so forth, all the way up to lime and limestone. Now that means you're going from your red fleshy stuff that is on the outside of your body more in towards your connective tissue and bones and organs, all the way up to the last thing here, which is limestone, which is really your tendons. That your tendons formed of limestone. And it's not marine looking limestone, which is the CaCO3 clear. It's CaCO3 called porphyritic limestone, which has all kinds of fibers and everything that is the structural part of tendons and connective tissue. It's basically fascia. will be involved in there as well, and kaolin clays, which are the red bloody investments. That's the difference between marine limestone and the type of limestone that is from creatures. Now let's go a little deeper into the chemistry. Okay, this is the chemistry of your body in chemical terms: silicon, calcium, magnesium, iron, and aluminum, and so forth. And there's all kinds of other metals in there that they don't show here, but these are the primary ones. They do the work in your body. Now, sandstone is a sedimentary rock, and it's eroded away skin cells, and that's why you see that silicon is extremely dense in sandstone, and that's because you're 50 times more silicon in your skin, the eroded part. Right? Then after you go past your skin, you get into mudstone, and that's the stronger fleshy part. It's still mud, and it's still red flesh, but it's the mud stone. It's not the eroded red skin. And you see, now you're missing all that silicon is gone, because now you're into the fleshy part. And of course it's gone here because you're still in the limestone is your tendons. Now you see all these other different chemicals that have eroded off of your skin cells and so forth. Very little calcium. You see Ca calcium, very little calcium, because that's your skin. But when you get into your deeper parts of your body, you have a lot of calcium in your bones and in your connective tissues. So this tells the story of the rocks. Sandstone is the skin and the eroded areas of your body that are they were touching the water of the floods. And it's 50 times more silicon in your skin than anywhere else in your body, so that's why you find all the silicon is eroded out and in the sandstone. Then you get into the mudstone, and it shows its chemistry of the flesh and of the organs and so forth are all in here, and those do the more work. Then you get into your limestone, which is your tendinous material, your hard, tough CaCO3 material. That gives you stability and structure to your body. This makes your body work and does the work of your body. This is the structure of your body. This is the presentation of your body to the rest of the universe. And that is what erodes. And in the Great Flood, it eroded all of the creatures, basically most of the skin cells off them, because you very rarely find the skin intact completely, although I have a lot of them that have that. But skin does erode away, and that's what the sand is. So this is the chemistry of the bodies of creatures. Let's just finish up with this, because this is the opals. Now, opals are a special case in mud fossils. They are mud fossils because they are created in wet environments, but it's not wet of water. This is wet of blood. What happens is, this is a particular heart, but all kinds of opals, any creature can become opalized if it is in blood, and it petrifies in blood. It stabilizes in blood. And this is critical, because remember I talked about how important the transition metals are. This is the proof. This is the proof right here. There's your blood. It's red. You see this here? This is like the lining of your heart, your ventricle of your heart. And I believe these might be the little heartstrings. But you see the specific color that particular type of tissue wanted to take on. And it only wanted to take that on because it needed a specific molecule to bond with it. And that's the green. And it might be copper, it might be vanadium, who knows what it is. But it's probably a combination of things. But the point being is, if this thing here is looking for this exact same color here and here and here and here and here, because it's the exact same tissue, that means that this is a specific tissue that requires a certain type of transition metal in your blood to service that particular exact tissue. And if that tissue was now yellow, you would know that the transition metal that was supposed to be turned to blue is missing. Or the bacteria that was supposed to accumulate the material that would make that turn blue is missing. Or whatever you took into your body didn't have whatever metal is required to make that turn blue. All right, so I hope you understand what I'm saying. Everything has its own color, and that means it has a requirement for a certain transition metal. And if you don't have the right bacteria, and if you don't have the right food, and if you don't have the right metal in your body, that thing is not going to pull in the heart the way it's supposed to, and you're going to not be pumping well. It's as simple as that. And all of that stuff is involved in your blood. And you see all these different little colors inside your blood. I believe the blood itself shows it's packed with all these colors. You see? You see the colors up here? That's all I can tell you. I see this. And then when I look into the lungs, I find that the lungs have their own specific combinations of colors. Very, very intricate combinations. Not just simple... here, I'll show you right here. If you can see those different colors, that's lung tissue. And those colors are very different, and they mean that there's different chemistry in the different little vessels of the lung. And they do not understand that either. This is a lung as well. And it's very hard, I'm sure, for you to see those different colors. But if I put that in water, and if I put it under a microscope, you will see that each one of these little balls has its own specific chemistry. So I think there's more going on in the lungs than just transferring oxygen. There's something else is going on here with this chemistry. There's another lung that is, you can see it has different metals and shiny things going on inside here. There's a lot of action going on inside that we don't understand, I believe. And there would be a lot more information and health if we did understand the processes that are happening here. Because as you saw in that heart, this is very, very specific areas that have very specific requirements. It's not just you pour a bunch of this stuff in, everything's fine. And this right here, as you can see, this also is a lung. And this lung has, you can see the little tiny holes in there. That's where the blood is. There's little pockets of blood that run through there. But the black and the red is the blood that's running out from this lung. This is not just a rock that is leaking this stuff. It's a lung that has now showing what it was leaking out. And the red and the black is always the blood. So I guess I'm going to leave it at this. But if you start looking around, you'll start seeing things that'll make sense to you as you pick them up and look at them. Okay, I guess I'll leave it at that for today. But here's another one. It's a good one. Mud fossil identification and process. And I've got all kinds of videos on blood from rocks and, you know, pliable stone built the ancient world, and megalithic seamless perfect explained walls, exquisite details of anatomy and mud fossils. It goes on and on and on and on and on. So all I can say is, if you're interested, there's plenty here to look at, and I'm trying to make it as, you know, easy as I can. It's a tricky thing if you don't understand chemistry. It really is. It's not, but it's not. But chemistry is very simple to understand. You know, I show this stuff over and over, and I try to make it simple, but I hope you find something in it. And here's one that latest discovered a humanoid examined by MudFossil University. So there's a lot to look at here. All right, so I just hope you enjoy it, and we can reach truth in what we're looking for, because this is not a monkey bone. It's not just something silly. There's a lot here that's very, very important, not only to today's information, but it could play out in your whole life. There's a lot here to think about.